Hey guys, my name is Zach Lasseter, and I'll be discussing a lab I did about Newton's second law. In the lab, I observed the motion of a tennis ball that was moving at the same speed without changing direction. I captured the video of the motion and then analyzed the video using Tracker in order to extract the object's position and corresponding time. I then constructed a computational model that accurately described my observations based on Newton's second law using VIDLE. And to see how close my observed results were to the predicted results, I plotted the observed position versus time and the predicted position versus time on the same graph using Excel. Here we have two equations I used in the lab. The first is Newton's second law equation of final velocity equals initial velocity plus net force divided by mass times delta t. The second equation is final position equals initial position plus average velocity times delta t. Both these equations will later be used in the Python code for the computational model. Now let's head over to the tracker demonstration. Here we have a tennis ball that will be moving in the positive x direction. First thing I gotta do is put a calibration stick on the tennis ball that measured the diameter of the tennis ball, which was 0.067 meters. I then had to put the tennis ball at the origin of the graph. Now I'm going to play it, and as you can see, as the tennis ball is moving, it's moving in the positive x direction with a constant slope, meaning constant velocity. And as the tennis ball was moving, Tracker was recording the position values for random time intervals. Now let's head back over to the PowerPoint. Here we have code that was used for the computational model. Here we have the mass of the ball is 0.056 kilograms. Here we have the initial position of the ball as 0.001 meters in x. And here we have the initial velocity of the ball as 1.758 meters per second in the x. The initial velocity was calculated by taking two positions and taking their difference and dividing it by the change in time for those corresponding position values. Here we have a while loop used in the code. Its while t is less than 0.633 seconds, which is the last time recorded for the last position in Tracker. Here we have a fnet equals to 000 because we're assuming it's a constant velocity. Here we have Newton's second law equation written out again, and as well as the position equation. Here we have the graph of the position versus time of a tennis ball, comparing observational model and the computational model. The observational model differs slightly from the computational model, mainly because it's impossible to make the fnet equal to 0 due to things like you couldn't completely capture the tennis ball when it was moving at constant velocity because it could have been decelerating or accelerating in the time period at which I analyzed it. Now let's head over to the Python code. This is the Python code that was used for the computational model. Got it from a Python shell. And once you run the model, you will get two graphs. This one represents the tennis ball moving in the positive x direction, and this graph right here represents the position versus time graph moving in the positive x direction with a constant slope, meaning constant velocity. Okay. Other things to consider. What if we were to flip the axes? If we were to flip the axes, the velocity would still be the same magnitude, but would be going in the opposite direction. In our case, it'd be going in the negative x direction instead of the positive, but would still have the same magnitude. Is it possible for you to say how many pushes and pulls are added together to give zero net force in the case that we observed? Yes, because in the upwards direction you have a normal force, and in the downwards you have gravitational force. Those two cancel each other out. In the negative x direction we have a friction force, and in the positive we have in the positive x we have a forward force, and those two cancel each other out. As far as this goes, this lab did prove that Newton's second law equation was accurate, because if fnet was truly 0, the initial velocity and final velocity would be the same. In our case, it was really close, even though it wasn't a perfect scenario. Thanks, that's all I have for this lab. Until next time.